All right, so good afternoon again. Thank you for coming. And this is really more like a high-level review session for all the sections. So I will start maybe with my part, and then if you guys want to ask me questions during any point, you can feel free to interrupt. I don't mind. And try not to put your question on the chat. I may not be able to actually distract myself to really look at the chat very often. So anytime you want to ask me questions, you can feel free. Okay, just interrupt me. That's fine. Okay. The main thing is really to give you some idea about assignment number three solution because that's the main coverage. Well, that's the only coverage for the coming programming test too. Let me just start by some administrative issue here so everybody can be aware. So I just confirmed again about the test for different section. The day is really the same as before. That one doesn't really change. I just want to emphasize that somehow the lab space availability has been quite limited for next week. So we were not able to really get a full hour because of the constraint. So we got actually some other courses, they got lab tests right after. So we are just not able to do the like a 1 hour or even 17 minutes like a last time for all the sections because all the sections are coordinated. We just need to be the same. So what we do instead is to say for every section we got 50 minutes for you. However, don't worry, you're not gonna be given like a three problems like a last time for programming test one. You will be given two problems to solve, which I can tell you briefly about. So both of them will be about the trees. Okay. So depending on your section, you can take a look like which day and which time you should go to. And the venue is just the same. Okay, WSC 105, 106, 108. There's no seating plan. You can go whichever room you like. But normally we want to fill out 106 and 108 first. And like what I said, 50 minutes, but the number of questions and also level of difficulty have been adjusted accordingly. So don't worry too much about you're losing some time. Well, not really, because we can reduce the number of questions from three to two. So that's still within reasonable. And for policy, it's really the same as last time. I'll let you guys read it. You should, just to get familiar with the policy. And of course, the percentage over here should not be surprising. It's just on the course syllabus, right? And then the structure for the test will just be the same. You're going to use the Eclipse, and you will be fully responsible for writing your Java program without any compilation error. And also, you need to make sure you submit in time. Okay. If you cannot really submit all the files for grading, there's simply nothing we can do. So you really got to make sure you do that during the test. All right. So this one is something you also want to go over. I can just go over very quickly with you, but you got to see the detail. You will be given two problems. Both of them will be about a tree. Roughly speaking, you can say they should take you around equal amount of time, about 20 and 25. It could be 25 and 25, etc. One maybe they are not identical, so naturally one will be more difficult than the other. They might involve also array list and also hash set. So as I mentioned over here, I'll point to you. Give me one moment. So definitely you gotta use a tree node and SLL node that you kind of use in your assignment number three. So that one is no surprising. And the only two classes you can use for Java library, if you see applicable, it may be that you don't need them, right? So maybe in one of the problems there, you simply don't need any array list or hash set. Maybe just require some integer or maybe double. I don't know, something like that. But whenever you need any Java library classes, hash set and array list are the only two classes you can use. Guys, please, no math class. So we made it very clear you cannot use any other Java library class. Okay. You don't want to get any penalty because of that. So that's why I said you really got to be familiar with the policy. Okay. So you cannot use these classes. That's the same list as before. You can just get yourself familiar. And then other than that, rationale, etc. Okay, for the coverage, right? Assignment number three, you don't need to worry about assignment number one and two specifically. But of course, for assignment number three, that involves about SLL node. You have to know the basic about syncly link node and also the tree node for sure. That's kind of new stuff that we didn't cover in programming test one. And also all the basic methods for array list and hash set. For example, how do you create an empty collection? And also, how do you add some element into a collection? How do you check to see if some element exists in the collection? Things like that, right? The basic. Whatever you were expected to manipulate these two classes for programming test number one, you might need to do something similar for programming test two. All right. Right, so that's about the administrative side for the assignment for the programming test two. I'll pause here. Do you guys have any question? All right, if you do, you can please just speak up. Otherwise, I'll continue. But at least I hope that's clear. All right, hearing from no one. So let me continue. All right. So what I want to do is I want to give you guys maybe just like a reference pointer, just about different places that you can go to really review, to really get prepared for assignment. Sorry, for programming test two. And then I'll try to point to as many resources as possible. At the end, I can also maybe suggest something that you might still have some time if you want to dedicate a weekend or maybe even some part of the weekday. Of course, depending on which section you are to get prepared. Right, let me start with this fragment over here. So this fragment comes from your assignment. Oh, sorry. Let me just make sure. Okay. Whenever if my app has blocked, please feel free to let me know. Okay. Sometimes I may not be aware. Okay. Okay, so this fragment here actually comes from your assignment number 3 instruction PDF, right? If you missed that, I will highly recommend you try to review it, right, for the basic. And may not dive into detail, it's actually very straightforward description. Okay, the way to really review this is you want to put aside the starter code that we are going to give to you. Actually, that's something we give to you for assignment number 3. They will be given to you as well for the programming test 2. If you look at a practice test that I made available on eClass, you're also given these two classes, right? You're given the tree node and also SLL node. So these two are both generic. You can see the generic parameter right here, right? Let's review very quickly about the structure. For the SLL node, this one should be no surprise. You just is a singly linked node. So you got the elements over here, which can be anything. So for example, if you instantiate the E over here to be, let's say, integer, so E over here will be integer. But in our particular case for assignment 3, you can instantiate E to be a tree node, for example. In that case, each element will be a tree node, right? So that's the extra complication you want to deal with. But if if you have already completed the assignment number 3, you will be already aware of this extra complication. And then you got the next pointer, which will be point to another node, the next node, the successor, and you got the very standard accessor and mutators. So during the test, you can feel free to use any of the basic method that's given to you. However, you are not supposed to add anything or modify these two classes because when we grade your submission, we're going to replace these two classes in the test package by the original version. So don't really extend it, right? So these two, as is, should be enough for you to solve any problem you're given, okay? And then we look at the tree node over here. That's also generic. I can make it a little bit bigger, okay? You can see we still got the element here. Let's visualize a little bit. How about that? So if you think about the tree node, right? The tree node at the runtime, okay, is generic. So tree node. And then whatever parameter E here is going to be the data that we're storing in the tree node. For example, it could be, let's say, integer. I'll just say I, okay? And so there are 1, 2, 3, 4, 4 different compartments, what 4 different variables that's being stored, or attributes being stored in each tree node. Number 1, we got the parents, right? So you can think about we got parents, which you can think about visually is going to point upwards to the parents of the node. Of course, if the node itself is already the root, then the parents will just be null. Okay. And also we got also we got the elements over here, right? That's the data. So element here. So that'll be the data, which may be storing some integer, for example, 23. Okay. And then we got two things over here. We got SLL node of tree node and also SLL node of tree node. So think about each line over here is instantiating the generic parameter of SLL node over here by tree node. So tree node of E. What does that mean? That means when you say head of child list, it's like single node, like a head versus tail. If you say the head, which is referring to this particular SLL node, dot get elements is going to return a tree node. And then if you want to extract that particular integer inside, you got to say dot get element again, right? I'll write it down. So this is kind of manipulation you will be expected to do. So someone say you cannot really see the screen. I'm pretty sure I'm sharing. Okay, please double check, right? Okay. All right, let me just continue here. So for example, if you look at the head and also the tail, right? The name over here could be slightly confusing. Well, actually, it's not really confusing. It already says it's the head and the tail. So that means head and tail, they are not storing the entire list per se. They're only storing either the beginning or the end node, right? It's a single node, okay? So here, if you think about right here, let me just say head, okay? If I say head over here dot get elements, head dot get element is going to give you a tree node of E. That one there is going to give you a tree nodes of E. But if you want to extract, for example, the integer that's inside over here, you got to go for one more level. In that way, you have to say head dot get elements, which will be a tree node, and then dot get elements. Okay, it's just natural because the structure. Okay, so you can think about like here. Let me visualize this. So let's say you got a head of the child node. That one there is basically pointing to a SLL node over here. And for the SLL node, you actually got element over here, and the element itself is a tree node. And the tree node over here might be storing some elements, for example, 46. So in order to get to this particular 46, what should you do? You should say the head over here, and then .get elements, which will give you the tree node, and then you say .get elements, which will give you the value over here. All right. So when you read over this paragraph over here in your assignment number 3 instruction, is saying exactly that, right? So that's something you should really read it over and convince yourself. All right. All right. It's a very quick walkthrough about what you're supposed to have read. If you haven't, you still have time, right? Just get it done. Any question about what I have said so far? Any part you want me to clarify? Okay, let's see here. Will the test consist of binary tree question two or just generic? Okay, you're asking two things. They are not necessarily related. First of all, the tree node we're going to give to you certainly will be generic, right? So all the tree question will be generic. And you're asking about binary tree. It's definitely possible. So the tree node that we are dealing with, it can be used to construct a general tree. And general tree means each node may have more than one, may have multiple child nodes, can be 2, can be 3, can be 4. So binary tree is just a special case for general tree. So binary tree is definitely possible in the question. All right. So in short, the problems you'll be given will be generic for sure. And also, you may be given problem for either general tree or the special case binary tree. Definitely possible. Yeah, I'm going to provide a recording. Yes, I'll do that. Tree node basically points to the head. The tree node over here, okay, let me just do a little bit more illustration for you guys over here. Okay, and I can point to you another thing that's more complicated. Okay, how about we do this? Okay, let's say conceptually you have this tree here. Let's say I got 23, and then I got 46, I got 69. All right. So first of all, let's start with the 23. It should be stored in a tree node. So this is a tree node, which will store some integer. And then you got element over here. Oh, let me put parent first. How about that? So the parent pointer over here is going to point to null. Right? It's a root. And then the element here is going to be 23. And then we got another two pointers. We got a head and we got a tail. Okay. So we got a head and we got a tail. And the head is going to point to, you know what, for my convenience, I might want to put the tail here and head there. Okay. So we got the head over here and we got a tail over here. Okay. So the head is going to point to some node that's going to represent 46. Okay, I'll get there in a moment. And also the tail is going to point to the end of the chain of node. In this case, we should get 2 because we got two children, 1 and 2. Right? I'll elaborate that in just one moment. Okay. So we got the tail, we got the head, and now how do we visualize these two? Okay. You want to think about each node here may have more than one children. And the way we store the child nodes is by using a linear collection, in this case, singly linked node, like a chain. So you can think about here, the head is going to point to some singly linked node. Singly linked node. And let me be more precise over here. Okay, it's going to be a singly linked node. Singly linked node. And then the E there, it will be a tree node of integer. All right. And that one there is going to store some elements and also next. Okay, let me put the next over here. And also it's going to store some elements. Since we got two child nodes over here, so there should be another next. Okay. So what we have is the next is pointing to the second child nodes. Well, the second node that stores the child node. And the next over here will just be null, right? What about the elements? The element is going to be the tree node. So what I will do is I'm going to copy right here. Okay, so that'll be the first child, and this will be the second child, right here. Okay, so this will be the first child, and this will be the second child. Okay, and of course, let me change the content here. Not 23. Okay, so this one here should be 46 and 69. 46 and 69. And then you can also set a parent pointer. It should be pointing back. For example, the parent should be pointing back to here, right? And also the parent should be pointing back to here. And also we got 46 and 69. So they're external nodes. They simply don't have any child nodes. So we got null here. We got null here. We got null here. We got null here. All right. So if you look at the diagram conceptually, you only got tree nodes over here. But at the Java runtime structure, you got some one extra layer which represent the linear collection that stores the child nodes over here. So that's really the visualization that you were supposed to grasp already in assignment number 3. Right? So this one really shows to you the tree nodes and also the SLL node really work together seamlessly. Okay. Okay. Right? Any question? If no, I'm going to continue. Okay. Another thing, you want to really study, that's also part of the assignment number 3. Okay, so I didn't have the file open, but I can mention here. So if you go to the assignment number 3 starter, all right, and if you go to the tests package, so there is one test case there. I forgot exactly what it is called, by something called tests. Maybe something like a trees.java. That one there illustrates to you how to construct a tree using the SLL node and also the tree nodes. So for those of you who want to look at, what if you got multiple level of the tree node, for example, how would the structure look like? So they over there, they do have some example over there. So you want to go over there and trace the code and then draw the diagram, right? So that would be the best way for you to visualize the structure here at the runtime. Of course, in the programming test, you might be given trees of multiple layers. So it's definitely worth spending your time figuring out. Okay. Okay, let's see this. Okay, the tail here is a reference to, of course, to this node over here, right? Over here. Yeah, so of course, you don't really need to know, but if you want to go into the SLL node class, you can definitely go into it and see how the get children method is actually implemented. That might just give you a little bit more insight about the structure. Okay. Can we have a SLL node of children such that the first element is null? I'm not exactly sure what you mean over here, but anyway, so you can I'll just continue first. Okay. All right, so that's about the administrative issue over here. Okay, and then let me just dive into a little bit more into the assignments. Okay. Great. So let me talk about maybe a different task over here. I'll just go over maybe the solution, make some annotation, and then we can talk. Okay. Just before that, let me just talk about the general idea for the two different tasks. Okay. I'll just mention them, but I mean not. So this structure over here is the exact runtime structure that you gotta understand. So that will actually help you when you actually program your solution. But when I kind of sketch out the solution at a conceptual level, we don't really have to go that detail. You just have to remember that the way to store the two child nodes over here is by using a singly linked node chain. Okay. All right. So let's now talk about the different task. Okay. For task number one. All right, so that one is really about, some particular ranks and you want to extract, the nodes from there. Okay. So let me talk about it at the high level about how you can solve it. So there are obviously two possible solutions. I think maybe the first one is what most of you will try at first. Okay. So the task number one, you were given some tree node n, and also you're given some range of the ranks, let's say I and also j. Of course, you're going to return like a singly linked node, right? So that's going to be the result chain of nodes. So there are two possible solutions over here. Okay, so the first one here is is the more straightforward, the more conceptually straightforward solution that you might choose to do because it has very clearly two faces. Okay, so the first solution would be, let's say, if you're given this, and then let's say n that you initially starting with is the root. Okay, and then phase number one, you're just going to somehow systematically visit all the nodes in the tree. And in this way, you can choose pre-order or post-order. Okay. So may not be in order because in order has the precondition that the tree must be binary. If the problem there doesn't really give you the assumption that the tree is binary, you cannot do in order. Okay. So here you can do either pre-order or post-order traversal. And if you look at the solution, it is trying to do pre-order, which means you gotta add the parents first into the chain, and then you're gonna recursively add the nodes in the subtrees rooted at the child nodes. And once you get the pre-order done, you will get some kind of a chain of list that's unsorted. Okay, so you're going to get some SLL node chain. So you're going to get maybe the beginning and also all the way to over here. So the number of nodes right here will correspond to the size of the tree, right? Which is linearize the tree structure, okay, using pre-order traversal. So that'll be step number one, right? So you can try to get let's say get phase A done. And once you have done that, you got some linear collection over here, and then you try to sort it, right? So B over here will be to sort this chain. The traversal result. And for the sort over here, of course, you can use any sort you like. At least we have already covered insertion sort, selection sort. That's quadratic. That's okay. But if you already know how to do other things like a merge sort with quick sort, it's okay too. But we definitely don't really restrict like what kind of sorting you can do. Okay, they can do, for example, let's say insertion sort or selection sort. So once you have sorted the chain of nodes, you're going to get some sorted chain of nodes of the same size. In that way, you can simply go to position I and position J, and then extract the nodes in this particular range, and you're done, right? So conceptually, three steps, basically, okay? And C over here is about extract the nodes from indices I to J, right? It's a conceptual sketch, right? Recap. You're given this tree over here with a node. That's the input to start with. And the first phase, you try to do some pre-order or post-order traversal to get all the nodes in a linear collection. And then the second phase, you're going to sort this particular linear collection. You can use, for example, insertion sort or selection sort. And once you got a sorted chain of nodes, you can actually try to extract all the nodes from that particular range of indices, I and J, which are the input, right? So it's it's definitely a very acceptable solution if you can make it work. But if you look at the solution, what we do is we try to combine basically A and B into a single step. We basically try to say when you try to do the pre-order traversal while you're doing it, you can somehow try to sort the resulting list at the same time. All right, there's a way to do that. Okay, so I'll just describe that very quickly. Okay, let's say number 2 here. So visually speaking, you're still given the tree, and then you got n over here, right? This is the same input. So we somehow try to come. The A over here is really the AB together. Okay, that one there is you're going to actually traverse, and then you're going to keep inserting the nodes into the right place so that the chain remains sorted. Okay, I'll write it down here. But that's something I can highlight to you as well when I look at this solution code briefly. Okay, so this one here, you're just going to traverse, and when each node is added, okay, so here I'm going to use a different color here, inserted such that the result chain of nodes remain sorted. So the difference is when you are doing the pre-order traversal for the first approach, you don't really care about sorting it, right? So there's no such step of insertion. But if you actually incorporate this particular insertion step over here, you can try to sort the list at the same time. So this is essentially a sub-step for the insertion sort. We're basically doing insertion sort while we are creating the list, right? So that's something you can dive into the solution code. I'm gonna highlight some segment to you so you can they can help you a bit. So once you're done with the A for approach number 2, and then once you get to B, it will just be the same. You will just have to extract the nodes from indices I to J, right? So whether you go for approach number 1 or approach number 2 is completely up to you. I would tend to argue that approach number 2 might be easier in the sense that getting the insertion helper method to really work might be easier than getting the insertion sort or selection sort to work if you compare the two, right? But of course you might find that this one might be a little bit easier, which is completely fine. All right, so that's task number 1. Okay, you can go for approach 1 or approach 2. But for most of the students who came to me to share their approach, I think they actually use approach 1. But for approach number 2, it's not really much more difficult. In some way, it might be a little bit easier. Okay. Okay, so that's about task number 1. And then let's talk about task number 2. And for task number 2, it's really about generating some string which contains 2 pieces of information, right? We got the size of the subtree, like a number of descendants, and also the sum of the values that's stored in the tree, right? So we got 2 pieces of information. Again, there are 2 ways for you to do this, right? I'm just going to mention them quickly, okay? Okay, for task number 2, which is to get the statistics from the input tree. Okay, let's talk about approach number 1. Again, the input is simply just the root of some tree, right? Just the root. We don't really have like a range anymore. That's only for task number 1. Okay. So what we get is, let's say the root, again, let's call it n. Okay. And of course, this is the input tree. Okay. If you prefer, you can say you try to do some pre-order traversal. You try to do some pre-order, post-order. I'll leave the choice to you. Okay. So let's say you do some traversal of the tree, but as you are visiting each node, you try to figure out both information at the same time. Okay. So we actually got first we got the sum of values, also the number of descendants. Right? So these are the two pieces of information we would like to get eventually, right? So for those of you who are able to make it work at just one pass, so you're just going to traverse the tree just at one go, and then you can figure out the sum of the values and number of descendants at the same time. That'll be okay. Okay. But that's not what the solution does. The solution tries to kind of separate these two calculations to make it a little bit conceptually clearer, which I'll go over with you. Okay. So after that, after one single pass, you will just get an output tree of the same size. And that one there will just contain both pieces of information. Okay. That's approach one. Okay. But for approach number two, it's gonna be a little bit different. We're still given the same input over here. And we know that we'll need this and this. So why don't we compute them separately? So what we do is we try to do some traversal of the tree the first pass and only figure out the number of let's say only figure out the sum of values. Let's say we do that. Okay. So we have some intermediate tree of the same size. Okay. You can think about this like a tree number one, and that one there only store the sum of the value, which is just this part here. And then for the second part, we just create another intermediate tree over here. Let's say T2. And that one there stores the number of descendants. Okay. So this tree contains the first piece, and this tree here contains the second piece for every node. And to really generate the output for ultimate return, what we do is we try to somehow say we start another traversal, but the traversal is going to keep two pointers at the same time. So you can think about this might be current number one, and this might be current number two, because we know these two trees have exactly the same structure. It's just that the data that's actually stored in the element might be different. One is about the sum, the other one is about the number of descendants. But if you try to really try to traverse at the same time, which you can see in the solution code. For example, let's say I look at the root over here. I can simply concatenate the sum and also number of descendants from these two nodes and make the string on the fly. And then when I go to for example, the first child over here and the first child over here, I know that these two nodes must have the corresponding information for the sum and also the number of descendants and etc. Right? So I can really, since I can make the assumption that these two trees are structurally just identical, in that way I can just traverse them concurrently. Okay. So once you have done that, you're just going to get the output tree of the same size, right? So that's the output. Right, so conceptually, this one here, you're right, we might take more space, but that's not really our concern. So our main goal for this assignment here, just for you to practice recursive thinking on the trees. So given the input, depending on how many pieces of information you might need, you can just create as many intermediate tree as you like. So for each one of them, it will be easier to calculate as opposed to if you try to calculate all the pieces of information at one go. Okay. So once you got the number of intermediate tree, you can try to traverse them concurrently, okay, at the same time, because we know they are structurally identical, and then you can get output eventually. Okay. All right, so just summarize about the conceptual approach for both tasks. So the solution actually give you this one and this one over here. But for this one and this one over here, if that's what you have done, you definitely want to make sure it works. And then you can also look at the solution to see how to solve the problem differently by another approach. Okay. Yeah, for programming tests, we don't really have any constraint on the asymptotic upper bounds. As long as your method terminates, that'll be fine. Correctness is a priority, right? You got to pass the JUnit test cases. But if your code takes way too long to really terminate, most likely it's not terminating, in which case, of course, you wouldn't pass any test cases. So there's no constraint on the space complexity, and there's no constraint on the time complexity. The most important thing is your code terminates and also your code pass the test cases. All right. Hopefully that's clear. Okay. All right. So guys, I think what I plan to do next, well, that'll be the last component I want to do today, actually. I just want to go over with you very quickly the solution code. So I may not actually trace them precisely. I think that's really something you want to dive into and really get to the logic for the code. I can just give you some highlights at a high level, which I think will be useful anyway. So what you should do, let me just give you some tips about what you should do moving forwards from today. You should really review any missing background knowledge you have about the tree nodes or the SLL node. If you're still struggling with this basic, it's definitely you have to get through them. Otherwise, there's no way you can actually program from scratch, on your own on your test day. So catching on the basics, that'll be number one. And number two, you want to make sure you're able to do the assignment problems on your own, in the sense that maybe either you already pass all the test cases of your own solution. That's okay. You don't necessarily have to look at the solution we provide to you. Or if you didn't pass anything, let's say before the submission deadline, but you just want to study the solution, that's fine too. Okay. But ultimately, you want to set some timer for and simulate the test session. You can simply log into the remote labs. We kind of gave you the simulation steps, right? In a programming test one. I didn't repeat the information this time in the PDF for programming test two, but I can go back to the PDF. So you will log into the remote labs, and then you're going to download the starter code for maybe the assignments or maybe for the practice test, and set yourself some timer. For example, let's say 90 minutes, right? But for assignment, you can make it maybe a little bit, if you're only practicing the first time, you can make it a little bit longer. But hopefully, eventually, you will be able to solve both problems, within 50 minutes. Okay. So that's kind of what I would suggest. And then let's say you have done with all I have said already. You're in a very good position. At least you have grasped all the basic. But if you want to practice more, you can feel free to go to, there are tons of resources really on the web about tree problems. It's not like a unique problem we are trying to have you solve. So you can definitely feel free to go to a website like a LeetCode or any interview problems website. So they usually got a category for just trees, right? You can go to the tree problem there. So the only thing you have to be careful about is usually their tree node class or SLL node class may not be identical for of what you're given in this course, right? So what you got to do is before you solve the problem from any external resources, you have to really adapt the node class, like a tree node or SLL node class to what you're given for this course. Otherwise, it's not so relevant to the programming test too, right? So different things you can do really before your test day. Okay. Okay, so let's now take a look at the solution very quickly, right? So let's, I don't want to drag everybody too long. So let's see if we can do this within 10 or 15 minutes. Okay, let's take a look. Right, the solution is already given to you. You can download it and take a look, and also for the practice test. So for the practice test, I may not touch that today because I think you guys should really give it a try and then look at the solution. Okay, so let me start with the first task, right? And as I mentioned earlier, the first task, we are basically using approach number two. So we try to traverse and also do the insertion, kind of insertion sort at the same time. Okay, I'll point out to you the places that you gotta watch out for. Okay. Okay, so let's start with this. So the method that we are talking about is this method here. Okay, hopefully that's big enough. Okay, so get elements of ranks, right? So there's a method you're programming, there's a public method, and we actually got some helper method right here. Get sorted list from, and then you can see whatever root that we're given, and we pass the root over there. So this is phase number one. The phase number one is actually going to just, the phase number one is actually going to traverse and insert and sort at the same time. And phase number two will be to go for that indices, right, for that range. Okay, let me just show you exactly how to understand the phases. So think about phase number one is right here, just this line, because it's making a helper method call. Okay, so this one here is phase number one, which is traverse and sort at the same time. Well, we'll look at the helper method in just one moment. Okay, look at phase number two. That one's very easy to see. So phase number two is really this part over here. Okay, starting from this all the way to over here. Okay, so this is phase number 2. So this is phase number 2, which will be to extract. You can, well, extract nodes from indices I to j from the sorted chain of nodes, because phase number 1 has already sorted that while traversing it. Okay, let's look at phase number 2. Phase number 2 is a very conceivable loop that you can learn from assignment number 2, right? So that one there, you're just going to go over the chain of nodes from phase number 1 from the beginning until the end. So the critical condition you got to get right is over here, right? You want to make sure the loop counter over here, when the loop counter I is actually in between the low rank and also upper rank. And in this case, you're going to somehow keep building a new chain of nodes to extract them. Okay. When the loop counter I is in the range, extract the nodes. Exactly how to extract the nodes, you can look at the code in detail. Okay. All right, so that's about phase number 2. Okay. So for phase number 1, how exactly do we actually traverse and also insert at the same time? Okay, let's now take a look. So for that one there, okay, let me see over here. So the method, we got 2 methods over here. We got get sorted list from, which is being called, from the original method. Also, this one here also calls get sorted list from helper. Okay, get sorted list from helper. So this is the recursive method that we are implementing, right? So the natural way of solving any problem on the tree for sure would be in the first instance recursive algorithm. So this is the recursive helper method. Okay, we'll see that in a moment. And then you will see that we also got some the root over here, right? That's the same tree being passed. That should be no surprise. And also we are initializing some node that's actually, you can think about the start is going to be the start of the sorted chain eventually, right? So this one here is going to be the start of, how about this? I don't want to, I want to be more precise. Okay, this start will be some node to start building the sorted chain. However, it is important for you to notice this helper method here itself is actually going to return an SLL node. So the node that's being returned, for example, you can see that is going to return the result. So when you study this code over here, you want to see exactly how the result is being reassigned or initialized, right? That's something you want to pay attention to. So here you want to think about the entire method call is going to return some SLL node. Okay, I think that's more accurate of saying that. Okay, not necessarily the start you're actually initially passing, not necessarily. Okay, so this one here is going to be the head of some of the sorted chain. So once this recursive helper method return the sorted chain, you're gonna assign it to here and then return. Once this is returned, you can see you can go back to phase number 1. So you can return to sorted list and you can move on to phase number 2, right? So that's kind of the flow. All right, so let's now take a quick look on how the recursive helper method is being implemented. Let's find out where the recursion is being made. Where the recursion happens. So if you look at get sorted list from helper, it appears only once in its implementation, only once, which is right here. Okay. We are basically doing some in order, I beg your pardon, not in order. We're basically doing some pre-order traversal. Okay. Okay, so I just want to remind you over here. So here, this is basically the pre-order traversal. Why is that pre-order traversal? Because this part over here is really about the children part for the pre-order. Remember, for pre-order traversal, we get to visit the parent first, and then we visit every child nodes of that particular parent, right? So this will be the pre-order traversal, but it's more for the children part, which is very standard. You basically just set the head of the children list, and then you simply just call the get sorted list helper on each of the child, right? Call on each one of them. And then just move on the pointer. Make sure you can go the child from child number 1 to child number 2 and to child number 3, etc. Right? So this part here is very standard use of the singly linked node. Okay. And the one that's very long over here, okay. So this part over here, starting from right here all the way to over here, this is also part of the pre-order traversal. But that one there is about the parents. So parent itself is actually the node we are dealing with currently, right? So once we're done with dealing with the parents, we just do it recursively for all the child nodes. Okay. So this is the pre-order for the parents. Okay, we can dive a little bit deeper into it. Okay, let's do that. Okay, I can highlight some stuff to you. Okay, you will see that over here. Okay, let me first of all point out the following. Okay, so there is some if condition here. We say if current, the current is really the SLL node we're passing, right? You can see here we initially passing some start over here, and for the start, it stores null for elements and also the null for the next, just to begin with. Okay. So here we're saying if current element is null, that really means you can think about it. That means the tree that we are looking at the top node at the moment. That's the very, very first time we are hitting this if branch, only once. Okay. If this is the very first root, the absolute root that we're dealing with, in that way, we are just going to insert the absolute root as the beginning of the sorted chain. We do it only once. And the else part over here implicitly tells you that we are actually dealing with, for example, somewhere in the tree. For example, it may be this particular node over here, and underneath it, you may have some other subtree, right? So this will be basically the node that we're dealing with. Okay, so this is, we will see that it's n. Okay, I'm going to point out to you where n is. This one here. Okay, okay, let me not write it here. Okay, right here. So this is basically n is the root of some subtree. Okay, just that n is not the absolute root. Okay, absolute root is only deal with only once, because after that once, we guarantee we don't have this kind of null and null situation anymore. Okay, and then you want to watch out for the insertion itself. You can think about the while loop over here is really doing some insertion step to make sure the root is actually inserted into the sorted chain so that the resulting chain also remains sorted. Okay, I'll talk a little bit more about it. So this part over here is really about, okay, so over here. This one here is to insert n into the sorted chain so that it remains sorted. Okay, I can briefly sketch the idea very quickly. Okay, you will see some critical variables. So you will see things like you can see the previous over here. That's really important because whenever you want to insert like a node in between well, if whenever you want to insert into a singly linked node, since you don't have the previous reference, so you will need a previous node. I'll visualize that in just one moment. Okay. So the previous node here is very important. And then what we're doing is we basically have, let's say, imagine that this is the chain of nodes you have right here. Okay. Okay, right here. And then let's say we want to insert n into it, but where exactly should we insert it, right? So what you will see is when you study this fragment of code over here, what it is trying to achieve is you will insert the n into right here if the following. Okay. So think about this is like the previous node that I highlighted to you, the previous. And this one over here is the current node that we are using to traverse the list, right? It's called current. Okay. So the idea would be we try to somehow insert this one here to here and also insert this one here. That's what we want to achieve. But how exactly? What will be the property? Okay. So the property would be the n dot get elements should be larger than the previous dot get elements. And also n dot get elements should be less than or equal to current dot element. Of course, that's not exactly the right syntax. I'm just trying to explain to you the concept. So if you look at exactly how we use the different if then else over here, what we're trying to achieve is we want to find out the right spot for the previous and current so that the n falls exactly in between based on its value. So if we insert n in between these two nodes, the previous and the current, then the resulting list after the insertion remains to be sorted. So that's exactly what an insertion sort would do. Okay, so when you study this fragment of node, that's something you want to pay attention to. Okay, one more highlight for you. Okay, one more. Okay, so you also want to pay attention to the result over here. Okay, if you look at the result over here, and also you can see there is a special case where we're going to say result equals n. Okay, and also notice that we also got result being passed in the recursive call. All right, you can feel free to try replacing this by just the current. It's not going to work. That might be something you want to maybe use a breakpoint and debugger to find out exactly why. Right? It's also a very important insight into programming with aliasing, in object-oriented programming. It's not going to work because the current is not necessarily the head always. Okay, I'll just write down the reason. But what you really want to do is you want to focus on the result being assigned, first of all, and then you want to see exactly how the result may be reassigned. In which case, once this is reassigned, that means the result will be the head of the sorted chain. Okay, so that's why we get a passive result over here. That's a correct implementation. But you can try it out. Try something like replacing this by some other variable. It's not going to work. Okay. All right, so that's about a very quick walkthrough about certain important details about the task number one. Of course, it's not complete, not meant to be. So you really want to kind of understand conceptually what's going on and study the code in detail by yourself, and then use a breakpoint debugger or visualize, draw some diagram to really trace to understand it. So once you have got grasped the idea, you can definitely try to do it on your own from scratch. Okay. Okay, let's now do the highlights for the second one. Okay, very quickly. The second one conceptually is very simple. So this is really not much I should say. I'll just point out what you should really watch out for. Okay. So for second task, I'm following approach number 2 right here, right? So I'm given the input tree over here. I'm basically going to have two helper methods. Helper method number 1 is going to create some intermediate tree number 1. Helper method number 2 is going to create the second tree. And then I'm going to concurrently try to traverse this tree together and generate the output. I'll show you quickly how it is done. Okay. Okay, let's see. That's a task number 2. So the method we're implementing is called getStats right here. Okay, so we got two helper methods here. We got getSizes over here. So getSizes is over here. And then we got getSums. That one there is over here. So you may want to start with studying getSizes and getSums. So these two share almost the same block of code, but basically they're trying to do some traversal over the input tree and extract the information. And this one is going to extract the number of descendants for each node. And this one here is going to extract the sums of the data values for each node, right? Individually. The structure is really similar, okay? And we're going to get the intermediate tree. One is called the root of sizes, right? That's the first intermediate tree right here. The first intermediate tree right here. Okay. And then also we got this one here, root of sums. So that will be the second intermediate tree right here. Okay. So what should we do now? Well, once we got the two intermediate tree returned, we should now try to traverse them at the same time and get an ultimate output. So that's what the remaining code will do. So that part there is about get stats helper. And this one here is also recursive, right? And this one here, you want to pay attention to these 2 pointers. You can see we got current size of child and also current sum of child right here. Okay, so what you should do is, pay attention to how these 2 references are used to traverse the 2 structurally identical tree concurrently at the same time. That's fine. Right, so that would be something you will have to look in detail, right? Exactly over here. Okay, so this is the part you want to look into. All right. Or you can see here, we actually try to move these 2 pointers at the same time, right? You can definitely see, for example, you can see this one that get next, right? And also you can see this one that get next, right? We really try to move the 2 pointers synchronously, basically. Okay. All right, so that's about task number 2. Okay. All right, I think we're running a little bit more over time, but if you got any questions, I'll be happy to answer anything.
I was gonna ask for for both tasks, right? If you go
Yeah,
to the iPad notes, where you drew the diagram, is there a difference between the runtime for like your solution, like the 2 solutions for each
yeah.
task?
Are you talking about task number 1 or task number 2?
For both of them, like there's 2
Mhm.
approaches. Would there be a
Okay.
difference in runtime?
It's a good question here. Let's say for this one here, there's really no difference. If you talk about space complexity, of course, this one is gonna waste a little bit more space. You gotta have some duplicate of tree, but space is not really our concern, right here. So if you talk about running time, it's really the same. Because for this one here, if you try to extract both information at one go, you're still gonna, there's no way around. You have to visit all the nodes right here. So that's gonna be big O of n. And this one here, you basically just gotta do more traversal. So you're gonna do traversal number one, traversal number two, and roughly traversal number three, right? In that way, well, it's a big O of roughly 3 times n, but it will asymptotically it's still linear. So both approaches don't really matter which one you use. So you choose the one that's more conceptually clearer to you. That's for task number two. And for task number one over here, let me see. That one also wouldn't make a difference, I don't think, because the idea goes like this. Let's talk about this one here. Okay. For you to really traverse all the nodes, it's going to be big O of n because you're going to visit all the nodes and add them to the list, right? And here, when you say sort the traversal result, let's say if you choose insertion sort, it's going to be n squared. And then if you extract the nodes from index I to index j, the worst case could be maybe from the beginning, from the very beginning until the very end. It will be big O of n. So if you add them up, n plus n squared plus n will be n squared. So for approach number one, it'll be n squared, assuming that you're going to use some quadratic algorithm. But if you want to improve the performance, you can definitely use maybe merge sort, for example, if you want to. That's going to be n log n. So this one is going to make the algorithm get down to n log n. So that might be better. However, for approach number two, it's going to be also n squared. We don't really need to go to the detailed analysis over here, but intuitively, you can think about you're basically going to visit each node, right? So there'll be n nodes you have to really visit. And then for each node visit, you have to insert that particular node into the chain of nodes so that it remains sorted. And if you kind of think about how the insertion sort writing time is actually derived, if you try to insert for every node over here, you're still going to get like a n time, like a up to n for each for the most expensive insertion. In the sense that for the very last node that you want to insert into the sorted chain, you already got you already got n minus one nodes in the chain. And you want to insert the last one into it. So it's going to be causing n. So you basically got one and then two and then three all the way to n. So if you add up the cost, it's going to be n squared as well. Okay. So my point is, if you actually use the second approach, the running time will also end up to be n squared. So it will be the same as number one. However, if you actually use the merge sort or something that's better than n squared, then approach number one can be potentially more efficient. Can it make sense to you?
Yeah, thank you.
Okay, good. For recording, I will try. So I may have to get a process, maybe have my quick supper, and then I'll try to get it posted. I'll try to get it done tonight. If no, I'll definitely try early tomorrow morning. All right. All right, guys. Any other questions? Yeah, the difficulty level, yeah, will be similar to assignment number three. Of course, they are not identical problems. So some of them you might feel a little bit easier. Some of them, I don't know, maybe around the same. Some of them might feel a little bit harder, but it's around there. Assignment number three. So definitely want to make sure you're proficient in manipulating the tree nodes and also SLL node. I think that's the most important thing. Yeah. All right, guys. Thank you so much for coming, and then good luck. And then I'll see each one of you during your test session. And then good luck. And then we'll touch base later. Okay. Take care. Bye bye.